Welcome to the second half of the course, in particular to Lecture 7, The Human Factor. The title here is pretty much the theme for the rest of the course because we're now looking at what effect human beings have had on climate and what our evidence is that we are in fact influencing the climate of today. Let me begin with a quick review of a couple points made in earlier lectures. In the previous lecture, you saw the carbon cycle, the natural carbon cycle. You saw how carbon cycles between the atmosphere, living things, the oceans, the soils, and some of it is removed eventually into the deep ocean. You saw in particular a very important fact about the carbon cycle, namely that any additional carbon that gets into the ocean surface, atmosphere, biosphere, part of the carbon cycle remains there for timescales up to hundreds to thousands of years. Even though carbon itself lives in the atmosphere for only about 5 years, the rapid cycling means that any additional carbon we put into that part of the cycle will be with us for a long time. Earlier lectures showed also how atmospheric carbon dioxide levels and temperatures are very well correlated. And what that leads us to believe is that if we humans put additional carbon in the atmosphere, not only will it stay there for a significant time, but it will also cause Earth's temperature to rise. And without going into any more details at this point, I want to emphasize that that conclusion is basically physical science applied to a very simple system of the Earth and the atmosphere. Now, there are a lot of complications in that system. I can't tell you immediately how much the temperature is going to go up, but it makes perfectly good physical sense that if we put additional carbon in the atmosphere, it will remain there for a long time and it will cause Earth's temperature to rise. That rise in temperature associated with additional carbon dioxide, particularly in the atmosphere, is called the enhanced greenhouse effect. Where does this additional carbon come from? The dominant source of the anthropogenic carbon, the carbon that comes from human activities, is from burning fossil fuels. That's not the only source of the carbon, and that's not the only source of the warming, as we'll see in the course of this lecture. But the dominant source is the combustion of fossil fuels. Now, I'd like you to think back to the the diagram that I showed in the previous lecture of the carbon cycle. In that diagram, we had flows going between the atmosphere and the surface, between the surface and the atmosphere, between the plants and the atmosphere, and so on and so forth. We had one minor flow that I mentioned at the end that was very insignificant, at least in terms of the quantity of carbon involved, and that was the flow of carbon in the form of dead material that didn't have a chance to decay before it got buried and eventually became the fossil fuels. So there's a big reservoir of fossil fuels in the ground that contains a lot of carbon, about 10,000 gigatons, we think. That reservoir, under the natural state of things, just sat there under the ground. We humans have begun tapping that reservoir as the source of most of our energy, as I'll show you in subsequent lectures. And so what would you have to do to alter my picture of the natural carbon cycle? Well, you'd have to add an arrow coming from that fossil fuel reservoir and going up into the atmosphere. How big is that arrow? That arrow represents a flow of about 7 gigatons of carbon per year. So we human beings, through the burning of fossil fuels, are putting about 7 gigatons of carbon, or emitting about 7 gigatons of carbon into the atmosphere. We'd add another arrow to our diagram, an arrow representing the effects of deforestation. When we cut down forests and the wood subsequently decays, and the lack of the absence of the forest means we aren't taking carbon dioxide out of the atmosphere as much. All that means an additional roughly 2 gigatons of carbon is going into the atmosphere from deforestation. That number is less certain than the number from fossil fuels, and I'll give you reasons soon why we know so much about the fossil carbon. So we're talking roughly an additional flow of 9 gigatons of carbon from the surface into the atmosphere, or from the buried fossil fuel carbon, in that case, into the atmosphere as a result of human activities. Now, that flow, 7 gigatons of fossil fuel carbon, another 2 gigatons from deforestation, is pretty small compared to the magnitude of the carbon flows in that carbon cycle diagram. 110 gigatons a year, for example, from photosynthesis. So you might say, well, this is a minor effect. Why do we worry about it? And again, that's why I went into such detail in the carbon cycle last lecture. The reason this is important is because any additional carbon we put in the atmosphere, any additions to those flows, remains in that cycling system for hundreds to thousands of years. And so it accumulates over time. And so if we keep putting 7 gigatons a year of carbon out, much of that accumulates in the atmosphere and continues to build up and build up and build up. So it isn't that we've perturbed the carbon flows in just a small way. Well, we have perturbed the carbon flows in a small way, but we've done it in a system where the additional carbon accumulates over time. And we've been doing that since roughly 1750, roughly the start of the industrial era, when we started using fossil fuels wholesale. Now, what happens to that 7 gigatons of carbon that we put in from fossil fuel burning and the 2 gigatons from deforestation? Roughly half of that ends up adding to the atmospheric carbon. The other half is taken up by a combination of the oceans and soils, and exactly where it goes and exactly how much is taken up is a matter of current research still. But of the carbon we put into the atmosphere, roughly half of it ends up basically staying there in the atmosphere. Again, it goes through that rapid cycling, but the atmospheric concentration goes up, the atmospheric content of carbon goes up by about half the amount of carbon that we emit. And as a result of that, we would have to make one other change in that carbon cycle diagram. You may recall that the atmosphere was a reservoir of carbon with about 560 gigatons of carbon before the start of the industrial era. Today, and I don't know when you're watching this course, so today may be one date or another, and this number is always changing, but roughly at the time you're watching this course or hearing this course, we have about 800 gigatons of carbon in the atmosphere. That's a substantial increase from the amount there was before the pre-industrial era, in the pre-industrial era. And that's again because even though the carbon flows associated with human activities are relatively small in the global carbon cycle, they put additional carbon into the system that continues to accumulate. So the amount of carbon in the atmosphere has gone up substantially since pre-industrial times, and it's now about 800 gigatons. What effect does that have on carbon dioxide concentrations? Well, that increases the concentration of carbon dioxide in the atmosphere as well, and the increase in carbon dioxide concentration shows a rise from about 280 parts per million in the pre-industrial era to something on the order of 390 parts per million today. And again, that depends on what today means for you, what day you're watching this. Because the amount of carbon in the atmosphere, or the concentration of carbon dioxide in the atmosphere, is rising today at about 2 parts per million every year, give or take. Sometimes it's a little more, sometimes it's a little less, but it's about 2 parts per million every year. So at this point, it's somewhere on the order of 390 parts per million. You'll remember my milk jugs, parts per million simply mean if we had 1 million gallon milk jugs of air and we separated it out. In the pre-industrial era, 280 of those gallons would contain carbon dioxide. Today, about 390 of them contain carbon dioxide. That's a rise of roughly 40%. That's a significant impact we human beings have had on the carbon dioxide content of the atmosphere. And again, that couples with everything we know from the first 6 lectures that we expect a rise in temperature because of the enhanced greenhouse effect because of this additional carbon dioxide. Now, how do we know this history of atmospheric carbon? Well, I want to tell you a little bit about that because we have considerable confidence in these measures of atmospheric carbon dioxide. As I indicated earlier, it's pretty easy to measure atmospheric carbon dioxide in the past because we have bubbles of air trapped in ice cores, and that gives us a record way back, and I showed you some records, and I'll show you them again, that go back some 500,000 years roughly. In the modern era, we've done even better. Since about the 1950s, we've had monitoring stations at a number of places around the globe, and one of the most important ones is on Mauna Loa in Hawaii, sticking up 10,000 feet above sea level and sampling the clean Pacific air that isn't contaminated by being close to any major landmass, that's close enough to the equator that it samples air that's mixed from the northern and southern hemispheres, and so we believe gives a good indication of the carbon dioxide concentration of the atmosphere globally. And let's take a look at our data on carbon dioxide concentration in the atmosphere from the beginning of the industrial era, from about 1750 to the present. So I have a graph here which shows overall that rise in concentration from 1750 to about the present. That's a rise from, again, about 280 parts per million to the present about 390 parts per million, roughly. And then there's a little inset that shows the data from the year about 1960, just after we started this monitoring program on Mauna Loa. And this is data from the Mauna Loa measuring station. And what I want to emphasize about that is that we measure this data so accurately that if you look closely at that graph, you'll see little up and down wiggles. Those aren't noise. Those aren't random errors in the measurement. Those are the effects of the seasons. In the northern hemisphere, When spring comes, green plants come out, and the northern hemisphere has most of the land area of the world, so it has most of the green plants. And those green plants, through photosynthesis, take carbon dioxide out of the atmosphere, and as a result, in the spring and summer, the carbon dioxide content of the atmosphere goes down. And then the plants, winter comes, and the plants shut off much of their photosynthesis, and the carbon dioxide level goes back up again. And that's what's reflected in those little fluctuations. And the reason I'm showing you this is to tell you that we can measure with exquisite precision the carbon dioxide content of the atmosphere, and it is indisputable that that carbon dioxide content has risen by something between 30 and 40% since the start of the industrial era.